As part of your post lab, you need to create a data table that includes the gross flame color, wavelength, frequency, and energy of the photons emitted during each of the flame tests. You will need to create this data table on your own and import it into your Pages document. In the video that we just watched, we saw that there was a very strong red color that was being emitted when the unknown solution or unknown sample was being ignited. When you examine your data table that was provided along with your procedure and other instructions, you will notice that the red wavelength is equal to 701 nanometers. You are going to use that information in the next part of this problem to calculate the frequency of a wave. Before you can actually use that number, you have to convert it into meters. And we know that 701 nanometers is equal to 7.01 times 10 to the negative 7 meters. That is the number that we will take with us into the next part of this problem. Now that we know the wavelength of the red photons that were being emitted from our heated sample, we now need to calculate the frequency that is associated with that particular wavelength. In class, we discussed the fact that the wavelength is inversely proportional to the frequency, and the equation of C equals lambda nu. So wavelength times frequency is the equation we will use to calculate out this next part of the problem. C is a constant equal to 3 times 10 to the 8th meters per second. We know that our wavelength, based on our information from the data table, is 7.01 times 10 to the negative 7th meters. And then the other thing we talked about in class today was the triangle, the proportions triangle, and that was C over lambda nu. If we are trying to calculate the frequency, then we're going to take C and divide it by wavelength. So our equation that we are going to use, I'll write it up here, is frequency equals the speed of light divided by the wavelength. Setting this up, I get 3 times 10 to the 8th meters per second divided by 7.01 times 10 to the negative 7th meters is going to leave me with just 1 over seconds, which is the units of frequency, also known as hertz. When I plug this into my calculator, I get 4.28 times 10 to the 14th hertz. Actually, my calculator gives me 4.279600571 times 10 to the 14th, but we're going to round that to 3 significant figures, as our wavelength originally had 3 sig figs. We'll keep that throughout. So the frequency of the wavelength associated with red photons is 4.28 times 10 to the 14th hertz. We'll now use that information in our final process to calculate the energy of the wave that was emitted. The last piece of information that you will need to be able to calculate for this lab is the energy of the photon that was released as the electrons were going from their higher excited energy states back down to their ground state. From our previous problem, we calculated that the frequency of a red photon was 4.28 times 10 to the 14th hertz, which can also be written as seconds to the negative 1 or 1 over seconds. And then Planck's constant is 6.626 times 10 to the negative 34th joules per second. To calculate the energy of the photon, you're simply going to take energy is equal to Planck's constant times the frequency at which the electromagnetic energy is traveling. When we plug that in or set that up, we have 6.626 times 10 to the negative 34th joules seconds times 4.28 times 10 to the 14th seconds to the negative 1. What ends up there is our seconds actually cancel out, and we're left with just joules, which is the units that we want for energy. Plugging that into my calculator, I got 2.84 times 10 to the negative 19th joules, rounding it to 3 significant figures, as I only had 3 significant figures in my frequency. My calculations are now complete. All I have to do now is go back and calculate the frequency and the energy for all of the other colors that I was able to see during the lab. So I should have a total of 6 wavelengths, 6 frequencies, and 6 energies.